Welcome. In this video, we will simplify and walk through Hy-MT2, the new family of fast-thinking multilingual translation models from Tencent Hunyuan. Hy-MT2 ships in 3 sizes, supports 33 languages, and goes head-to-head with some of the largest commercial translation systems in the world. Over the next 22 slides, we will unpack what these models are, how they are built, how they are benchmarked, and how you can train or deploy them yourself. Let us start with the basics. Chapter 1. What exactly is Hy-MT2, and why does the world need yet another translation model? Hy-MT2 is not one model, it is a family of 3. The smallest is a 1.8 billion parameter dense model, light enough to run on a phone or a laptop. The middle tier is a 7 billion parameter dense model, the sweet spot for a single high-end GPU. And the flagship is a 30 billion parameter mixture of experts model that activates only 3 billion parameters per token, giving you the quality of a large model at the cost of a small one. All 3 share the same vocabulary and the same instruction following style. Hy-MT2 covers 33 languages out of the box. That includes the big European languages like English, French, German, Spanish, and Russian. It covers East Asian languages, Chinese, Japanese, Korean, Vietnamese, Thai. It covers South Asian and Middle Eastern languages, Arabic, Persian, Hebrew, Hindi, Bengali, Tamil, and more. And it even covers regional variants like traditional Chinese, Cantonese, Tibetan, Uyghur, and Mongolian. One model handles all of them, in any direction, with no language pair-specific configuration. Tencent calls Hy-MT2 a fast-thinking model. What does that actually mean? It means there is no long internal monologue, no visible chain of thought, no thinking tokens that you pay for and discard. The model reads the source text and writes the translation directly. That makes the latency predictable, the cost predictable, and the output count predictable. And yet, in head-to-head tests, fast-thinking Hy-MT2 still matches or beats reasoning models like DeepSeek V4 Pro and Kimi K2.6. This is exactly what you want for real-time production: subtitles, chat, voice interpretation. Chapter 2. Let us look under the hood and see how these 3 models are actually built. The 1.8 billion and 7 billion models use a classic dense transformer. Every parameter contributes to every token. Simple, predictable, easy to deploy. The 30 billion model takes a different path, mixture of experts. It has 128 separate expert subnetworks, and a small router picks the top 8 experts to handle each token. The total parameter count is 30 billion, but only about 3 billion are active for any given token. The slogan is A3B, meaning active 3 billion. The practical effect: you get 30 billion parameters worth of knowledge with the inference cost of a 7 billion model. Here is the simplest way to run Hy-MT2 yourself. Pull the model from HuggingFace with Auto Model for vLLM. Use bfloat16, let device map auto-handle multi-GPU placement, and remember to pass trust remote code equals true, because Hy-MT2 ships with custom modeling files. Build your prompt as a single user message, apply the chat template, and call generate. That is it. The chat template handles the special tokens for you, and the only knob worth tuning early is max new tokens. For production, you have 2 great options. vLLM gives you the OpenAI-compatible HTTP API with continuous batching and tensor parallel sharding. SGLang gives you the same, plus radix attention catching that is especially good for repeated system prompts. Both work with the published Hy-MT2 checkpoints out of the box. No conversion needed. One important note on sampling: the dense models and the MOE model use different defaults. For the 7 billion and 1.8 billion models, temperature 0.7, top P 0.6. For the 30 billion mixture of experts, temperature 0.7, top P1.0, top KO disabled. Chapter 3. Translation quality is not just about word-for-word accuracy. It is about following instructions. That is what the IFMTBench benchmark, which Tencent open-sourced alongside the models, is designed to measure. IFMTBench measures 6 different kinds of translation constraints. Number 1, glossary compliance, where the user supplies a dictionary and the model must use the exact target term. Number 2, style following, where the user asks for a formal, casual, or literary tone. Number 3, background disambiguation, where extra context decides how an ambiguous word should be translated. Number 4, layout preservation, where the model must keep delimiters and line breaks intact. Number 5, structured data, where JSON or XML keys must stay in English while values are translated. And number 6, code and tag preservation, where the model must leave variable names, HTML tags, and template placeholders completely untouched. IFMTBench scores translations 2 different ways depending on the constraint. For mechanical constraints like glossaries, layout, structured data, and code, it uses gate scoring. A Python rule checks if the constraint was satisfied, returns a 1 if yes, a 0, no middle ground. For subjective constraints like style and background, it uses continuous scoring. A separate LLM judge rates the translation on a 5-point scale, which is then normalized to a value between 0 and 1. The split makes the benchmark both fast, because most checks are pure rules, and fair, because the subjective parts are scored by a model that actually reads the output. Running IFMTBench yourself takes about 3 steps. Install the requirements, point a .env file at any OpenAI-compatible API for the judge, and feed the benchmark your model output as a JSON file. Each line just needs an MD5 identifier, and the response your model produced. The runeval script then scores everything in parallel using 20 worker threads by default. Look closely at the multi-constraint formula. The final score equals the product of all gate scores times the average of all continuous scores. That means a single failed gate zeroes out the whole test item. It is brutal but realistic. A translation that drops a JSON key is broken. Full stop, no partial credit. Chapter 4. Now that we understand exactly what is being measured, let us look at how Hy-MT2 actually performs. Tencent's own evaluation, which is documented in detail in their technical report, shows 3 big results. First, the 7 billion and 30 billion models both beat DeepSeek V4 Pro and Kimi K2.6 in fast-thinking mode. These are not small open-source baselines. These are the leading frontier open weights models, and Hy-MT2 wins. Second, even the tiny 1.8 billion model outperforms major commercial APIs like Microsoft Translator and Dubao Translator overall. Third, the wins are not just on generic translation, they are on the hard subsets. Real-world business documents, domain-specific text, and the instruction-following set we just discussed. Why does a fast-thinking model beat a reasoning model on translation? Because translation is fundamentally a pattern alignment task, not a multi-step logical reasoning task. When a reasoning model spends 1,000 tokens thinking before writing the translation, most of that thinking is wasted. A specialized fast-thinking model can put all of its capacity directly into the output. You end up with better latency, lower cost, and equal or better translation quality. This is the same lesson we have seen with specialized models in other domains. When the task is well defined, beat the generalist. Chapter 5. One of the most generous parts of this release is that Tencent ships the full training pipeline. Let us look at how you would fine-tune Hy-MT2 on your own data. The repository ships 2 completely independent training paths, so you can use whichever fits your team. The first is DeepSpeed Native, just the HuggingFace trainer launched through the DeepSpeed CLI, with scripts in train/DeepSpeed_support. The second is a Llama factory wrapper, which uses Torch Run to register the Hy-MT2 chat templates and apply a handful of monkey patches before training begins. Both paths produce identical checkpoints. Both support full fine-tuning and LoRa. Both ship with 0, 2, and 0, 3 configurations. Pick the one your team already uses. Do not rewrite your training infrastructure for either one. The training data format is dead simple. Each line of your JSON file is a chat message list, one user message containing the full translation prompt, one assistant message containing the gold translation. That is it. No special separators, no system prompt required, no language pair metadata. If you want to teach the model glossary following, just put the glossary in line in the user message, exactly as a real user would. If you want to teach a particular style, describe the style in the prompt. The model learns the instruction following behavior from the format of the prompts you supply. If GPU memory is a problem, Hy-MT2 has you covered with 4 compression paths. FP8 quantization halves your memory, with almost no quality loss, and works directly with vLLM and SGLang. The GGUF format lets you run on a CPU, on Apple Silicon, or on Windows through llama.cpp. A 2-bit GUF variant compresses the 1.8 billion model even further. And the most aggressive option, the 1.25-bit STQ format from Tencent's own AngelSlim toolkit, compresses the entire 1.8 billion model to just 440 megabytes, with a 1.5 times speedup at Inference. That is small enough to ship inside a mobile app. How do you pick which Hy-MT2 to use? Here is a simple decision tree. If you need on-device inference, in a browser or on a phone, take the 1.8 billion model in 1.25-bit GGUF format, 440 megabytes total. If you have one workstation with one good GPU, take the 7 billion model in bfloat16 or FP8. It is the sweet spot for quality per watt. If you have a production server with 8 GPUs, take the 30 billion mixture of experts model. You get frontier quality at moderate cost. And no matter which one you pick, validate it on IFMTBench to make sure it actually follows the kinds of instructions your users will give it. And that is Hy-MT2 in 22 slides. 3 model sizes from 1.8 billion to 30 billion, support for 33 languages, fast thinking architecture, a rigorous instruction following benchmark, 2 complete training pipelines, and 4 levels of compression, all the way down to 440 megabytes. Everything we covered is open source, under the Tencent Hunyuan repository. Thank you for watching. This presentation was curated and simplified by Omar Hosni.